Well, thank you for coming to this section. And I'm Yu-Chen. I'm from National Taiwan University. It has been a long time that we haven't met, in the international conference. And I hope that this will be the first one to come. We will have more in the future to talk, to discuss about research in different conferences. My presentation today. From the title, it seems small to talk about the proposed lab Spliced inner hoops in the plus Hinge region of beams. But actually, this topic, this proposed lab Spliced inner hoops, are to solve a very big question that is currently facing the construction industry in Taiwan. This is the outline of my presentation. I will first talk about the background information of this research, about the code requirement and the common practice in Taiwan. And then I will talk about the proposed lab Spliced inner hoops to increase the constructability of the rebar cage used in the plus Hinge regions of beams of special moment frames. And then I will talk about the experimental verification of the proposed lab Spliced inner hoops, and then I will draw the conclusions. So if you look at the ACI 318 code requirement about the transverse reinforcement in the plus Hinge regions, then you will find that it is required by the code that you need to use hoops to confine concrete and the longitudinal reinforcement in the plus Hinge regions. And the Taiwanese design code is very similar to the ACI 318 code. So this is also required in Taiwan. And this is in Taiwan a legal requirement by the government. And when the hoops are required, then the code also says that you need to provide lateral support to the longitudinal reinforcement. So for every corner, longitudinal reinforcement and alternate longitudinal reinforcement, you need the lateral support from the hoops, from the ties, from the cross ties, in order to provide confinement and to prevent premature buckling of longitudinal reinforcement. And there's also a requirement about the maximum distance between an unsupported bar and a supported bar. It's 150 millimeters. So these are the requirements by the code for the plus Hinge regions of beams. And it's also specified in the code that the hoop can be replaced by so-called closed stirrup. It is formed by a cross tie and stirrups with the seismic hook at the two ends. In order to satisfy the code requirement about alternate bar need the lateral support. So in this case, when you have 7 bars, the longitudinal reinforcement, then you need not only the outer hoop, but also you need the inner hoop to provide enough lateral support. However, if you look at the construction practice in Taiwan, typically, they don't do like this required by the code. For constructability reason, to lower the cost of construction, they usually do only 2 outer hoops close by 2 cross tie. Like you see from here, that you can see these 2 are the seismic hooks of the outer hoops. And you can see also 2 cross tie. And then you can see many longitudinal reinforcing bars without lateral support provided by the cross tie or the inner hoops. This is a typical construction practice in Taiwan. Very difficult to persuade them to change in the current situation, because if you want to do like what is required by the code, the cost has to be increased by 30 to 50%. And not only the increase of the cost, but also the construction time will be longer, will be extended. This is something that a construction owner does not want to see, so between the cost and time and the legal requirement, very often they choose this one. So this research is trying to develop something to do this easily, easier, with a lower cost, in order to persuade the owners, building owners, to provide the lateral support required by the code for the safety of the building. So we first checked the literature, and we found that back in 1985, Professor Tanaka, at that time, already proposed a way to do the cross tie easier for columns. This is for columns. You can see that they use lap splice cross tie, and also they try to use lap splice outer hoop. And this is conventional hoops. This is with the 180 degree at the both end of the cross tie. This one is 180 degree one end and 90 degree at the other end. So this one conforms to the code. This one also, and this one is better than the minimum requirement by the code. And from the test result, they found that it's not a good idea to do lap splice for outer hoop. I think this can be, understood, because if you use a lap splice for the outer hoop, once you have the spalling of cover concrete under seismic condition, then you are going to lose the capacity of the lap splice. So this is not a good idea. However, the test result show that it's a good idea to do lap splice for the cross tie. The core concrete can protect the lap splice very well under seismic conditions, so that the cross tie can let the column to show a behavior similar to the conventional cross tie. That's from their conclusion. And Dr. Lee, in 2018, they not only try to lap splice the cross tie, but they also try to lap splice the inner hoop. We already know that it's not a good idea to do lap splice for the outer hoop, right? Because of the cover concrete spalling problem. So they try to lap splice the inner hoop. And then they found that from the test result, the column with lap splice inner hoop show very good behavior. Better than a conventional way with 180 degree seismic hook at the both end. So indeed, this is something that we can do to increase the constructability of the transverse reinforcement. At the same time, we can maintain the seismic performance. However, these studies are for columns. There have been no research about to use lap splice hoops for beams. The difference between beams and columns are the axial load. Usually columns have axial compression, which can increase the capacity of the lap splice. So when you have no axial compression, what would be the performance of the lap splice? Still something that we need to answer. We need to study. So in our research, we try to study the use of lap splice for the inner hoops of beams, and we checked the code of ACI 318. We found that in section 25.7.1.7, there is a provision about the use of lap splice for the hoops, but this is for non-seismic condition. And they draw this to show that this can be used for outer hoops. And we know that it's not a good idea to use this for seismic condition. And in seismic provisions, there is no any mentioning about the use of lap splice for the hoops. So there are two research gaps here. One is there's no research about the use of lap splice for the inner hoops for beams. And also, no experimental study to discuss whether you provide a lateral support to the longitudinal reinforcement is really necessary to ensure a good seismic performance of beams. A lot of research about columns, whether you should provide lateral support to every bar or every other bar. A lot of research on columns, but no research about this in beams. So this is another research gap that we need to address. So we planned this research with 4 specimens to answer the 2 questions. This one is a beam with the hoops conforming to the coal. Very standard way to do this. And this one is the one that the Taiwanese engineer, they do not want to use. This one, a lot of construction problems. And this one, the last specimen is the beam with the hoops commonly used in Taiwan. So you can see there is no lateral support for the intermediate longitudinal bars. These 2 are the beams with the lap splice hoops proposed in this research. So this is type 1 and this is type 2. So in type 1, what we do is that we have 2 U-shape inner hoop. For the outer hoop, still continuous, okay? This, you cannot do lap splice for the outer hoop. You can only do this for inner one, because the inner one can be protected by the core concrete. And in order for construction to be done easier, so we use a welded wire reinforcement. So we have these horizontal bars to weld, 5 or 6 or 7 sets of the U stir up together, so that in construction site, it's easy that you can place this one, the whole set, quickly into the plus hinge region of beams. And then you can place another one, and you can very easy to assemble them. This is type 1. In type 2, again, for ease of construction, we need some special arrangement of the reinforcement. So in this case, we have a chair-like lower part of the inner hoop, and then the corresponding the upper part. So this one can stand in the place, in the formwork, and so easy for construction. So this is type 2. And then we did the experimental study at Anchorage laboratory to check their seismic performance. And due to the time limitation, I will just show some of the result. And this is the damage condition of the 4 specimens at a 5% drift ratio. As you can see, that this is the control specimen with the hoop arrangement conforming to the coal. And you can notice that more damage occur in this side compared to this side, because in this side, you have the cross tie. Okay, so the confinement is not so strong like the other side. Okay, so so that's why you have more damage in this side. This side usually would be the upper side in the formwork for beam construction. Okay, that's why you need this cross tie to facilitate the construction. And if you look at this one, this is the beam with the 2 outer hoops typically used in Taiwan. You can see that at the 5% drift level, not only you have a very severe buckling of longitudinal reinforcement, it's actually more severe than this one. From the other angle, you can see that. You see that almost all the 5 bars, they buckle simultaneously compared to this case. This case maybe just 3 have a severe buckling. So this one, because of no lateral support to the longitudinal reinforcement, so they buckle very early and very severe. And so also you can see a lot of spalling of cover and core concrete in this case. In contrast, in these 2 beams, with the proposed lap splice inner hoops, you can see not only the buckling, not so severe compared to the other 2 specimens, and also the extent of buckling is shorter, because the inner hoop can provide better restraint to the longitudinal reinforcement to prevent earlier buckling, and also can limit the buckling range. And because of that, so the concrete is better also protected. And yeah, you can clearly see the damage difference between the specimens in this slide. So from the forced displacement behavior, you can also see the difference. This is the control specimen. And if you look at the theoretical behavior of these 2 specimens, you can see that similar behavior, and even better in terms of ductility, strength, and energy dissipation. slightly better. But if you look at this one is obviously worse than the control specimen. You can see that after 3% in the negative direction, that is the direction that you will impose compression to the cross tie. So after 3%, the strength drop rapidly. Usually we want to see you have a 4% capacity to maintain your strength under the cyclic loading. So this one is not having so good seismic performance compared to the control one. So this is, I think, the first time ever that we can really see the real performance of the beam with the hoops commonly used in Taiwan. And I hope that this one can raise some discussion about our construction practice in Taiwan. And maybe this is acceptable, for some condition. If you talking about maybe you don't need such a high ductility requirement, maybe this one is acceptable. And this one has a low cost and the construction time. So my conclusion is that, first of all, we developed some new way to do the inner hoops. The construction time can be shorter, easier to do that, and the seismic performance is even better than the conventional one conforming to the code. And we also proved that the one that is commonly used in Taiwan is not so good. But I know it's very difficult, still, even though I have the result here, to persuade the building owners to really follow the code. Still under discussion. That's my presentation. Thank you.